In this video, we are going to explore two different case studies of algorithms and discuss their impact on our chosen segment of society, cell phone users.
Case study 1 will focus on people who input important information such as bank pins or credit card numbers into their cell phones, mainly protecting and encrypting that information from being stolen.
Case study 2 will focus on people who enable location services on their phone and allow applications to use their location.
Intro to case study 1. In this case study, we will argue that the encryption done by the cellular message encryption algorithm is ultimately insecure. The CMEA algorithm is a byte-oriented block cipher with a 64-bit key. It takes an n-byte message, an 8-byte key, and outputs the corresponding ciphertext. CMEA consists of 3 layers corresponding to each for loop in the pseudocode. The first layer performs a nonlinear pass through the input, affecting left or right diffusion, changing one character in the input, which changes multiple in the output. Starts by calculating t based on the value of y XORed with I. Pi prime is then calculated by adding pi to the output of the t box. Y is then incremented based on the value p. T is calculated by the function shown below. The C in this function is the cave table. The cave table is an unkeyed 8-bit lookup table shown here. The second layer XORs the right half of the block into the left half. This operation is intended to propagate changes in the opposite direction of the first layer and is unkeyed. The final layer performs another nonlinear pass and outputs the ciphertext. This step is an inverse of the first one.
The paper on CMEA talks about certain attacks, such as the plaintext attack and the meet in the middle attack, which prove the insecurity of CMEA. The paper also argues that CMEA is its own inverse. This can be problematic at times because people who have access to digital scanners or are strong at technical skills can retrieve the sensitive data of the users rather easily. This not only puts the privacy of the users at risk, but also increases the chances of theft. To make CMEA more secure, a new improved algorithm was formed which uses a function with a random behavior and removes the dependency of the first entry. On top of this, the cave table is replaced by the XBOS of AES, which uses all the 256 possible outputs and forces the plaintext attack to fail. Lastly, the improved algorithm also prevents the meet in the middle attack by increasing the computational rounds of t from 4 to 8 by multiplying the t to itself. The improved algorithm fails all the attacks that prove the original CMEA to be insecure. This means that the CMEA with the changes described above can be more secure than insecure. Due to this, users can feel safe about the privacy of their data being inputted on the phone.
Case study 2 is based on an algorithm for tracking mobility patterns of cell phone users. The algorithm we are focusing on uses sectorized mobility patterns as well as random movement prediction to guess the user's next network location with a fairly high degree of accuracy. This algorithm uses cells to represent the different network locations, and each cell is split into no, low, and high handoff regions based on the relative signal strength of the networks. Cells are further broken up into 6 sectors based on which cell is neighboring that sector, as shown here. This algorithm also uses a sectorized mobility history base to track a precise pattern of mobility of the user to aid in prediction. For input, the algorithm takes in the user's current position and looks for a pattern of movement within the patterns recorded in the sectorized mobility history base. If a pattern is found, the next sector is given as the predicted cell for the output. Otherwise, the algorithm turns to random movement prediction, taking into account if the user is in the high handoff region and if the user is moving away from the current network cell. The algorithm then determines which cell the user is likely to move into and tells the network to prepare for handoff to that cell. This allows for efficient handling of reservation of resources for each network location, preparing for the network handoffs when they are most likely to happen. This allows for the quality of service to be preserved throughout the transition, which leads to a positive impact on cell phone users because they would not experience a break in service where a call may be lost or an application relying on a network connection wouldn't freeze up or quit.
While discussing all the perks of enabling the location services, it's sometimes not the best option. This jeopardizes users' privacy and can be troublesome if an unwanted person or party is granted access, which may include stalkers, criminals, terrorists, or etc.